Hello and welcome to I believe, the last video of this complex section. So, right now, up to this point, we've talked about imaginary numbers in general. What are they? We've talked about complex numbers and how they relate to all of our operations, addition, subtraction, multiplication, division. Now, what happens when you take I to bigger powers? So, as of right now, we know, let's just write down what we know. I is equal to the square root of -1, and therefore squaring it gets you back to the real number, -1. Now, what happens when you take that to the third power? Well, there's two ways you can look at this. If you're comfortable with the I notation, it's a little better. I cubed is the same thing as I squared and I to the first, right? If you remember, there's a rule that if you have two of the same base, you can add the exponents, meaning you can undo that as well. And we know I squared is -1, so what we get is a negative I. We get a negative I, which still does not exist, but in other words, you can write it as -1I. If you don't like that notation, then think of it this way. You've got the square root of -1 cubed, which again you can split. The second one, or the first one, square is going to cancel the square root. We're back to -1. The other one is still an I. You get -I. And so now we see that I cubed is equal to -I. The same idea happens with the fourth power. We either split it into two radicals or we split it into two i's, right? Both of each being squared. And we're actually at -1 times -1 back around to a real I. And we can create this kind of table you see on the next page. I to the 0 is equal to 1. I to the I is equal to I. Okay, but I to the first is equal to I to the second is equal to 1, and I to the third is equal to -1. If you want, you can add the fourth one. I to the fourth is equal to 1. But then notice that this and this are suddenly the same. I wonder what happens when we take I to the fifth power. Let's apply this idea to the fifth power. What happens? Let's see. Let's do the I version of this. Let's split this up into as many I squareds as I can. That would be 2I squareds and another I to the first. Okay. Well, I squared is -1. And so we end up getting 1 times I, which is I. Interesting. That's the same thing as I to the first. Let's see what happens when we go I to the sixth. Let's see, I can make that into I squared times I squared times I squared, right? 2, 2, and 2 makes 6, which each one of these would be -1. And we end up with -1, which is, I'm sorry, there's a typo here. That's a negative. Oh, you can't see it, but it's hidden in the equal, which is the next one in the pattern. Let's see what happens when you go I to the seventh. We have I squared, I squared, I squared, and another I. So we have this. We just saw that this is going to be -1, and we get -I, which is the next one in the pattern. I bet you if we do 8, we can get back to 1. Let's see what happens. Well, I can do I to the sixth, which we just found out is -1, times an I squared, which is -1. Look at that. It's back to 1. And so what's happening is what we call a modular system. Remember how, so look at how we count. We count up to 10. Right? And then we basically start over with a new decimal place. We go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But 10 is a combination of 1 and 0. We start over. We use a different decimal. This is what we call a base 4 system, meaning we go 0, 1, 2, 3, and then start over. Okay, there's only these 4 options. And so this we can use to calculate really anything. If I had I to the 12th power, I just need to figure out how many 4 cycles it's gone through. So let's take 12, divide it by 3, and I'm sorry, not 3, 4. I'm ahead of myself. Divide it by 4. Is it a 0? Is it a 1? Is it a 2? Or is it a 3? I can figure that out by dividing it by 4. I get 3, which is a whole number, which means I to the 12th is going to go through 3 full cycles, and it's going to land back on I to the 0. There is a remainder of 0 here. And so I to the 12th is going to be equal to I to the 0, which we saw from the pattern is equal to 1. So we don't need to sit here and calculate each one over and over again. We can just divide that exponent. We're actually going to change this exponent to something else, 37. What happens when you have I to the 37? 37 divided by 4, because of the 4 options, we would get 9.25 if we did the full math. In other words, we get a full 9 with a remainder of 1. We get a remainder of 1. Think of it like quarters, right? Think of it like money. You have 9 and 1 quarter. If I had 9.5, that'd be 9 and 2 quarters. My remainder would be 2. If I had 9.75, that would be 3 quarters, which would be remainder 3. Okay. All right. So that means this is 9 cycles through, which, okay, cool. But really what's more importantly is it's now also 1 step into the next cycle. And so I to the 37th is equal to I. And that's all it is. We can do the same idea with even the huge ones. We're not going to sit here and calculate I out to 438,698th power. We're not going to do that. That's silly. Let's take 438 and 659 and divide it by 4. What would that be? Even I don't know that off the top of my head. 438,659 divided by 4 is 109,664.75, which means it's 109,664 cycles through. But who cares? It's like a spinning wheel. We don't care how many times the wheel spins. We just want to see where it is in the next spin. It's 3/4 of the way through the next spin. And so this remainder would be 3. In other words, this is equal to I to the 3rd. See that? And what is I to the 3rd? From the pattern, we saw that equals negative I. And that is our pattern. All right. What happens if you go the other way, though? What happens if you start going down and you do negatives? Well, luckily, the pattern follows the same. Remember what happens with a negative I? You would go 1 over I squared. That's one way to look at it. Another way to look at it is you've got I to the negative first times I squared. Okay, so we're going to go with the same pattern we did before. I to the negative first is 1 over I. That's just universal law. I squared is negative 1. And so you get negative 1 over I as your final answer. Cool. Down over here, I to the negative first. Well, we just did that. 1 over I. Sweet. Over here, we've got this really large number. Let's first take out the negative, which we can do. Negative 1 times I to the 3855. Okay, this is 1 over I. We would want to rationalize these. Sorry, I'll come back to that. But let's figure out what is 3855 divided by 4. 900. So 3855 divided by 4 is 963.7. Oh, okay, I'll write it down here. 963.75. Which means, great, it's 963 ways into its next cycle, but we really care about the remainder. So this is equal to I to the 3rd. Now that is a negative I, so we have negative I over I. What does that do? Doop, negative 1 as our final answer. All right, let's go back a minute. These two are not rationalized, so we need to rationalize them real fast. We multiply by another I. Both sides, that gives us a negative 1 on the bottom, a negative I on the top. In other words, it's equal to I. Here we multiply by another I on the bottom, multiply I on the top. We get I over negative 1 or negative I as our final answer. Cool. Yeah, don't forget to rationalize. Even I do sometimes, but let's make sure we rationalize so that we can get the easiest to write answer. That's it for 8.5. Very long section. I'll give you that. Very long, but almost nothing new. This last part, definitely new. This, what is an imaginary number? Maybe new, right? Maybe. We already kind of had a concept on that, but complex numbers, addition, subtraction, multiplication, division, rationalizing, all of that is exactly the same as when you deal with a binomial. So consider these binomials. I'll see you again in the next video about solving radical equations. See you there.